Okay, this next chapter is a little bit different. We're going to be using some of the topics that we've talked about previously, but we're going to be applying them to fluids. And so this is a chapter devoted to the study of what's called fluid mechanics. And fluid mechanics is about how forces and motion work when you're dealing with fluids. Now, I want to be specific because when a physicist uses the word fluid, it can mean one of two things. It can mean either a liquid or a gas, because it turns out that liquids and gases have a lot of similar properties to one another. They also have things that are different about them, but what we're going to be doing is focusing on how they're similar to one another, and when you're looking at common features, you can refer to them as fluids. And so unless I specifically say otherwise, everything that we're going to be talking about in this chapter is going to be applicable either to liquids or to gases. Now, here we have a table that's taken from your textbook, and it's nice. It shows densities for lots of different materials. Now, to remind you, the formula for density is mass divided by volume. And so it's going to have usually units something like kilograms over meters cubed, because a volume is going to be something like a length times a width times a height. And so meters times meters times meters gives you meters cubed. So you can see kilograms per meter cubed. And in our table here, we can see that's the unit for these densities of different materials. And so we can see that we have solids, we have some different liquids, and then we have gases. Now, solids, of course, have the biggest densities, generally speaking. There are exceptions, but you can see that these solids all have high densities, comparatively speaking, for the most part at least. One exception that we'll talk about later is ice. That is, water ice has a kind of a low density, which is kind of interesting, but most of the other solids have pretty high densities. Here we have some liquids, and they have high densities too, but not as high for the most part. And then we have air. And so compare the densities of air. You have dry air, like the air we breathe. That's 1.29 kilograms per meter cubed. If we compare that to gold, gold has a density of 19,000 kilograms per meter cubed. Quite a bit more dense. And some gases even have lower densities than that. Helium, for example, you can see is a tiny density. Hydrogen, even less so. Very, very tiny density. But if you need to know what the density of something is, you can look it up in a table like this. In fact, there are entire books that are essentially just lists of densities of different materials. Or you can often find the density of something just by a Google search. If you for some reason need the density of something like silver, you could Google density of silver and it would come up and tell you what that was. So let's look at our checkpoint here. We can check our understanding on some of these things. So question number 1 says, which has a greater density? 1 kilogram of water or 10 kilograms of water? And the answer is water has the same density. If we look at water here, we can see water at 4 degrees Celsius has a density of 1,000 kilograms per meter cubed. And that's the same for however many kilograms you have. So the density of these materials is constant. It doesn't change. And so it doesn't matter whether you have 1 kilogram or 10 kilograms. Now, the next question is which has the greater density, 5 kilograms of lead or 10 kilograms of aluminum? And so the 5 kilograms or the 10 kilograms doesn't matter. The question isn't about the mass, it's about the density. And so we can look up aluminum and we can look up lead. And so over here in our chart, we can see aluminum has 2,700 and lead up here has 11,000. So obviously lead has a greater density than aluminum. And finally, we have what has a greater density? An entire candy bar or half of a bar? Assuming the candy bar is uniform, then it doesn't matter whether you have the entire candy bar or half of it. It's going to all have the same density on average. Now we're going to be talking about pressure, the pressure that a fluid exerts on something in the fluid or on the walls of the thing containing the fluid. So we need to understand what pressure is. And so pressure is defined as force divided by area. And so we can see here a couple of examples to illustrate a difference in pressure versus force, because people tend to mix these concepts up. Pressure is obviously related to force, but it's not equal to force. It's equal to force divided by area. So I've got two physics books here, the green one and the blue one, and let's assume they're basically the same mass. They're the same book despite the different colors, but one of them is laid on its side and one of them is stood up on its end. And so the question is, which of these is going to exert a bigger force on the table? Well, if they're the same mass, they're going to exert the same force, right? M times little g, that's the weight. That's how much force is going to be exerted. But what's the pressure? Now that's different, because here, that mg worth of force, that weight, is distributed over the entire area of the surface of the book here, whereas that same weight for the blue book is distributed over the smaller area of contact with the table. You can see that this guy takes up much less area than that guy, and so the force is concentrated over a smaller area. If you divide by a smaller number, the pressure goes up. So even though these have the same weight, this guy, the blue one, is going to exert a much bigger pressure. Over here on the right, we see another example, the simple idea of pushing a thumbtack into a board. And what's going on here is, again, you're pushing with a certain force and you want the thumbtack to go into the board. You don't want the thumbtack to go into your finger and cut you. And so you can see that the thumbtack has a cap here, so that has a very broad area. So the finger is pushing with a certain force, and that force gets spread out over the whole area, so the pressure gets less because you're dividing by a bigger number. But at the point where the thumbtack is making contact with the board, it's come to a sharp point. So there's very, very little area of contact with the board. And so all that force gets concentrated. You're dividing by a much smaller area, and when you divide by a smaller number, that makes this thing bigger. So the pressure is way higher at the board, and the thumbtack is able to insert into the board rather than into your finger. Even though we know from Newton's third law that the force pushing down on the board and the force pushing up on the finger, they're going to be the same force, equal and opposite, right? But the pressure is very different, and that's what creates the different effect. Now, there's something about pressure that's very unintuitive. And so here we've got two lakes that are dammed up. One of them is a very large lake, and you could imagine extending way off to the left. It doesn't matter how far it goes. And here we have a very small lake, but it's much deeper. In fact, it's twice as deep. This one's 3 meters deep. This one's 6 meters deep. And so which dam has more pressure exerted against it? Now, most people, if they didn't know the answer already, if you just ask them which one do you think has more pressure, they would imagine the large lake has more pressure because it's got more water that's being held back by the dam. But actually, it doesn't depend on how much water is there. What matters is how tall it is, the depth of the pond. And so liquid pressure, it depends on the weight density of the fluid and also the depth of the fluid. Now that's a weird word. What is weight density? I just told you that density is mass divided by volume. Weight density is a special kind of density which is related, but it's, instead of being the mass divided by the volume, it's the weight of the fluid divided by the fluid's volume. So, and again, that's generally going to be a constant number. And so you have the weight per volume times the depth. That's the weight density times the depth. That's how you determine the pressure exerted by a liquid. Again, the most important factor is not how much water there is, but what the depth is. And of course, a more dense fluid is going to exert more pressure as well. That's what this term is telling you. Now, when you insert an object in a fluid, and again, that could be you in a room filled with air, the air being the fluid, or it could be this prism here submerged under water, for example. The fluid exerts a pressure against the thing that it is submerged in it, but here's the rule: that pressure is always perpendicular to that surface. And so whatever irregularly shaped object you have, at the point where the fluid is in contact, it's always exerting a pressure perpendicular to that surface. Now, over here on the right, we have another diagram which shows a few interesting things about pressure. So you can see there's this glass, it's filled with fluid, and there have been some holes punched into it, maybe with that thumbtack we had in a previous slide. And so the cup of fluid, the water here, is leaking out. Now, there's a couple of things to note. One, this glass has got a slope to it because the bottom is more narrow than the top. We know the pressure exerted on the fluid at any surface, including the hole there, is always going to be perpendicular to that surface. And so you can see that these fluids, as they leak out, they're going to come out with a slight downward angle. And this one's got less of a downward angle than that one because there's more slope here. Now, what you want to also notice is that the one at the top, you might think that it would squirt out and go the farthest, but it actually goes the least far. The one at the bottom is the one that goes the farthest. Why do you think that is? Well, it's because the lower you go, the more pressure there is. And what causes that? It's basically the weight. The pressure at this point right here is caused by the weight of all the water, or whatever fluid it is, above it. And so if you're down lower, there's more weight of more fluid pushing down on you, and that creates a deeper pressure at the bottom. You guys probably all know that at the bottom of the ocean, there's a lot of water pressure. It could actually, physically harm you just by squeezing you. So that's why, because the ocean is so deep, when you go diving, if you dive down really, really deep, you'll feel that pressure because of all the weight of all the water that's above you. And of course, if you go higher towards the surface, there's less water above you and less pressure. Now, we just talked about how the deeper you go in a fluid, the more the pressure is. And so if you have something that is submerged in a fluid, the pressure exerted by the fluid on the top of the object is going to be less than the pressure exerted on the bottom of the object. That means there's going to be an upward pressure, a net upward pressure on the object. This is what we call buoyancy, and it's why things are easier to lift if they're submerged in a fluid, because the fluid is kind of helping you by creating this upward pressure. And so we call that, there's like an effective force pushing the object up, and we call that force the buoyant force. Now, one key concept that we have to understand in order to understand buoyancy is the amount of water displaced by an object. So imagine that you had a beaker that was filled up to the tippy top with water, completely filled to the brim, and then you submerged a stone in it. What's going to happen? Well, some of that water is going to slosh out of the beaker, and here's a little spout, so it'll come into this container here, and you could actually measure how much water poured out when the stone was submerged. And the trick is that the volume of the water pushed out would be equal to the volume of the stone, because we can see the water still up to the brim at the top. And so this is called water displacement. And again, the key idea is that when you submerge something in a fluid, it displaces a volume of the fluid equal to the volume of that object. Now, if the object is placed in a container of fluid that's not filled up to the brim, what's going to happen is the water level is going to rise. And again, that displacement of water is going to be caused by the volume of this object, the stone in this example, and that's going to displace a volume of fluid equal to the volume of the stone itself. And in the caption, we can see another way of saying that. The raised water level due to placing a stone in the container is the same as if a volume of water equal to the volume of the stone were poured in. In other words, if there was no stone and the water was just filled up to this dashed line, we could pour some extra water in, and that extra water would be the volume of the stone. Now, if I don't pour the extra water in and I put the stone in, the water level is going to rise to the same height, equal to the volume of the stone. That's how much water gets displaced. Now, the guy who discovered how this principle works is a famous Greek mathematician and scientist named Archimedes. And Archimedes came up with a principle to describe how buoyancy works, and that principle is called Archimedes Principle. It came historically, the king of Sicily, where Archimedes lived, King Hiero II, he posed a problem to Archimedes. The basic idea was this. He had commissioned his goldsmith to make a gold crown for him, a crown that was made out of pure gold. And he worried that maybe the goldsmith was trying to cheat him, like maybe the crown was 70% gold and 30% lead or something else. And so the question that the king posed to Archimedes was, how can you tell if the crown is pure gold or if it's an alloy of gold with some cheaper metal? In other words, the king wanted to know if he was getting ripped off, right? And so he posed this question to Archimedes. And so Archimedes spent a long time thinking about maybe different ways of testing the crown. And of course, you want to be able to test the crown without destroying it. You don't want to cut samples out of it or something like that, because then you would damage the crown. And so Archimedes thought about this for a long time. And according to the legend, he basically was unable to solve the problem, and he decided to take a bath and relax. And so he drew a hot bath, and he climbed into the bathtub. And as he lowered himself into the water, he saw the water level rise, just like we were talking about. And he had that flash of insight where he understood that the volume of the water displaced is going to depend on the volume of the thing displacing it. And he could use that fact to prove whether the crown was made of pure gold or not. And so he got so excited he wanted to go tell the king. According to legend, he yelled "Eureka," which translates to "I figured it out." Literally, it means "I found it." And then he ran to tell the king. But he was so excited and so eccentric, he forgot that he was naked, and he was like running through the streets of Sicily naked, trying to get to the king to tell him that he'd solved the problem. So what is Archimedes' principle? It says the buoyant force, that's that force exerted by that pressure difference on an object, on a submerged object equals the weight of the fluid displaced by that object. In other words, let's look at this scenario. We want to look at the weight of a 3-kilogram object. So we have this 3-kilogram object, and this is before it's been submerged in the water. And so we have this 3-kilogram object on this scale, and it's reading 3 kilograms. Then we lower it into the object. There's going to be a buoyant force, and that buoyant force is going to make it weigh less relative to the scale up here. And so you can see it's gone from registering 3 kilograms, now it only registers 1 kilogram on the scale. Now, if this container is filled to the brim with water, as you submerge the weight, the water pours out into this second pan here, where it's being weighed, and guess what the weight is? It's going to be the difference. 2 kilograms of water are displaced. In other words, the weight of 2 kilograms of water, that's the amount of weight that is the buoyant force. So the weight of the displaced fluid equals the weight of the buoyant force. Now, it can be a little bit confusing. It's not the weight of the object or the mass of the object that relates to the buoyant force. It's its volume. It's how much fluid is going to be displaced. And then once you know how much fluid is displaced by the volume of that object, you weigh that much fluid. And that weight, the weight of the fluid that's poured out, the displaced fluid, that is the weight of the buoyant force. And so here we can see you've got 3 kilograms worth of mass. You lower it into the water. it reads 1 kilograms worth of mass because there's 2 kilograms of weight's worth of buoyant force pushing it up, and that's 2 kilograms of the water that was displaced by the object. So it's not the mass that's 2 kilograms, it's the water that's 2 kilograms. That's how much the buoyant force equivalency is. And here we have some quick check our understanding checkpoint questions. So question number 1 says, does Archimedes' principle tell us that if an immersed block displaces 10 newtons of fluid, and 10 newtons is the weight, 10 newtons of fluid, the buoyant force on the block is 10 newtons? That's exactly what it says. The buoyant force is equal to the weight of the displaced fluid. Question 2 asks, a 1 liter container completely filled with lead has a mass of 11.3 kilograms and is submerged in water. What is the buoyant force acting on it? It would be the buoyant force would be equal to the weight of 1 liter of water. Of course, we know water is H2O, and the weight of 1 liter's worth, that's how much the buoyant force would be on that lead. Now, the third question says, a boulder is thrown into a deep lake. As it sinks deeper and deeper into the water, does the buoyant force on it increase or decrease? And it's kind of a trick question. The answer is neither. Why not? Because the volume of the boulder isn't changing as it sinks. And so how much buoyant force is applied to that boulder? It's the weight of however much volume that boulder takes up in the fluid, the amount of fluid it displaces. And if the volume doesn't change, if the amount of space it takes up doesn't change, then the amount of fluid it displaces won't change either. And what's the buoyant force? It's the buoyant force on the weight of the fluid. Now on this side, we can expand on that idea a little bit. Here we can see in figure 513, we have a block of something that's sinking, and we know that as it goes down to lower and lower depths, there's more and more pressure. And so you can see here we've got 1 arrow on top and 2 arrows on the bottom, so there's 1 arrow's worth of extra pressure pushing up. Down lower, the pressure is everywhere greater, so at the top we've got 3 arrows worth of pressure pushing down, and we'll have 4 arrows pushing up. What's the difference? Here, 2 minus 1 gives you 1. Here, 4 minus 3 gives you 1. It's the same difference in pressure all the way down. Here, there's more arrows, but the difference is still just 1 arrow pushing up. The amount of the buoyant force doesn't depend on how deep you are. It only depends on what the volume of the object is and what the weight of the fluid is. That last one, the weight of the fluid, all that means is that the buoyant force would be different in water than it would be in, say, liquid mercury, which is more dense. Liquid mercury, a liter of liquid mercury weighs a lot more than a liter of water, so something submerged in mercury would feel a much bigger buoyant force. Now, how is it that something like a ship, like an aircraft carrier, can float? If I have a block of iron and I dump it in water, guess what? That block of iron is going to sink to the bottom. Why? Why is it going to sink? What are the forces acting on it? We've got the force of gravity pulling it down, and we've got the buoyant force pushing it up. Here, the buoyant force is not strong enough to balance the gravity, and so gravity's a bigger force, and it sinks. How can we increase the buoyant force? Well, we can increase the buoyant force by making the object, in this case the iron, displace more fluid. If it displaces a greater weight of fluid, it'll feel a greater buoyant force. And so here you can see it shaped to displace more volume, and the corresponding buoyant force will be bigger, and it'll be strong enough to match the force of gravity to keep it from sinking. That's how ships float. Because they take up more volume, they're designed to be hollow, so they take up more volume, so they displace enough water so that the buoyant force can match their weight and keep them from sinking down. And here's the basic principle of flotation. A floating object displaces a weight of fluid equal to its own weight. And that is the basic principle of how things float. So here in the last slide, in this part of the lecture, we have this scale to measure the mass, and we've got a beaker filled to the brim with water, and we put a block of wood. Now, wood is less dense than water, so it's going to float. But the part of the wood below the water, that has displaced some of the water. And so some of the water is going to pour into this cup down here. And we know that for a floating object, it's going to displace a weight of fluid equal to its own weight. So if I were to get the weight of this fluid in this cup here, I would know that that's how much the block of wood weighs. And those are the basic ideas of buoyancy and Archimedes' principle.